This video provides an overview of antenna diagrams of radar sets. Different tasks and technical equipment can result in various antenna patterns for radar antennas. One such pattern is the fan beam, which has a narrow aperture angle in the horizontal plane and a wider aperture angle in the vertical plane. This pattern was commonly used in early two-dimensional surveillance radars, but nowadays it is only found in low-cost radar sets. The fan beam could be rotated by 90 degrees and was used by older height finders with a nodding antenna to search for the third spatial coordinate. This up and down pivoting pattern was also known as the beaver tail pattern. Nodding height finders and omnidirectional rotating radars work together in a network to jointly measure three-dimensional coordinates. In air traffic control, the precision approach radar uses both diagrams to safely talk down the approaching aircraft. Both diagrams swivel in a small sector to detect whether the approaching aircraft is directly on the glide path. Performing a narrow pencil beam would be too time-consuming for air defense or air traffic control radar. Such a scan can only be afforded by meteorological precipitation radar. In weather radars, the complete volume scan, which involves successive rotation of the antenna at several elevation angles, takes around 5 to 15 minutes. In air defense radar, multiple pencil beams can be generated simultaneously using digital beamforming. However, this involves significant technical effort and is still too expensive for air traffic control radar. To generate the most efficient spatial scanning pattern for a 2D radar, a cosecant squared pattern can be produced by modifying the reflector with a parabolic antenna. For short-range air traffic control radars, waveguide slot antennas are commonly used. However, they typically only generate a fan beam pattern. Slot radiators are essentially gaps or openings in an electrically conductive surface that can be considered infinite. As per Babinet's theorem, they are equivalent to a half-wave dipole in their function. Unlike a vertically aligned dipole with vertical polarization, vertical slot antennas provide horizontal polarization. Slots milled into a waveguide wall are fed by the wall currents of the wave propagating in the waveguide. By slightly tilting the arrangement, the radiated power can be regulated, resulting in a more even distribution. The more slots milled into the waveguide, the higher the antenna gain and the narrower the antenna pattern becomes. The distance between slots should be half a wavelength to feed all slots with the same phase shift. However, this calculation should use the wavelength inside the waveguide, which is slightly larger than the wavelength in free space for the same frequency. A change in frequency can cause a phase difference between the slots, which leads to an electronic sweeping of the main direction of radiation. This feature is called a frequency-steered phased array, abbreviated to FSPA. In air traffic control management, this technology is used in precision approach radars operating in the 10 GHz range. The longer the waveguide, the more slots can be milled into it and the narrower its horizontal antenna pattern. Common lengths range from 3 to 12 feet. The horizontal aperture angle is often smaller than 1 degree. The typical antenna pattern is a fan beam width vertical half power beam width between 20 to 30 degrees. By adding reflector plates above and below the waveguide, the beam can be made even narrower. With modified reflector surfaces, cosecant squared patterns can also be achieved. A cosecant squared pattern is generated with special forms of parabolic antennas or array antennas. It allows a situation-adapted radiation distribution and comes closer to the concept of ideal space scanning. It is therefore particularly suitable for air traffic control and air defense surveillance radars. Ideally, a cosecant squared characteristic ensures that an airborne target moving towards or away from the antenna at a constant height or altitude produces an echo of constant amplitude at the receiver input. The cosecant is a rarely used trigonometric function and is equal to the reciprocal of the sine. From the sine of epsilon, which is equal to the opposite cathetus, represented by height, h, divided by hypotenuse, represented by slant range r, it follows that the range, r, is equal to h multiplied by the cosecant of epsilon. We are now looking for the received power at the input of the receiver. According to the basic radar equation, this is proportional to the square of the antenna gain and inversely proportional to the fourth power of the slant range. The input power at the receiver must remain constant at a constant height or altitude. Therefore, the ratio of the antenna gain squared to the fourth power of the distance must also be constant. This implies that the antenna gain is proportional to the square of the slant range. We can replace the slant range with the term height multiplied by cosecant of epsilon from the first equation. A target moving towards or away from the antenna at a constant altitude should produce an echo with a constant amplitude at the receiver input. This means that the height has also a constant value. It can be eliminated from the equation without altering the proportionality. It remains that the antenna gain should change in proportion to the cosecant squared of the elevation angle. We have thus derived the mathematical description of the antenna. Surface Movement Radar, abbreviated to SMR, or Airport Surface Detection Equipment, abbreviated to ASDE, is typically mounted on high masts or even on the roof of the tower. A simple fan beam pattern can result in a wider blind spot. However, this blind spot can be reduced by using an inverted cosecant squared pattern, which can be achieved by installing an antenna with cosecant squared characteristics upside down. The advantage of this is that now a vehicle moving towards or away from the antenna produces an echo of constant amplitude at the receiver input. An inverted cosecant squared characteristic is also useful for coastal defense radar and navigation radar on ships. Two reflector modifications can be made when designing a cosecant squared characteristic using offset parabolic antennas. One option is to bend the upper edge of the reflector backward, as shown by the dotted line in the picture. However, a more common modification is to bend the lower edge inwards, which results in a smaller and lighter reflector compared to the other modification. The reflector can be fed using a horn radiator as a point-like source, which results in a double curved shape of the reflector. Alternatively, it can be fed from a linear slotted waveguide array, which results in a single curved reflector known as a cylindrical parabolic reflector. This inward bending can be clearly seen in the antenna of the ASR/NG terminal area radar from Hensoldt. The red antenna above the parabolic reflector is part of the monopulse secondary surveillance radar, abbreviated to MSSR. The four rods around the antenna are for lightning protection. You might also visit the radar tutorial on the internet. It is easy to find using the keyword radar basics, and no matter which search engine you use, it will be listed first in the results. Thank you for your attention.